Hi everybody, my name is Eric Fredericks, and together with my co-authors, I'm very excited to bring you our paper on a proof of concept for introducing self-adaptation into video game logic. Now, I've got a link to the preprint here on Archive and also a link to our game as well. It's live on GitHub pages. One thing that I'll point out, turn off the logging feature if you just want to play this for fun. It's a little checkbox that you can disable. Basically, it just stops a giant log file from being downloaded to your computer every single time. But other than that, I'll show you in a moment the game. What this is motivated by is basically my passion for developing at least little hobby games and my research background in adaptive systems. And I wanted to bring those two together for this paper. And honestly, I've been looking for a way to, make hobby game coding part of my job because that's always more fun than standard coding. Anyway, this is a visual of our game. So it's called Fish. It was based on some old Flash games. One of them that I at least am aware of is called Fishy. Basically, you are a tiny fish. You eat smaller fish to get bigger and bigger and bigger, eventually taking up the whole screen, and then you win the game. The idea here is to take at least our interest in, arcade games, game development, software engineering, and also creative coding, which is something that we are kind of interested in here at our university, basically to get away from the standard intro to Java, intro to Python, that kind of thing. Let's, maybe explore something a little bit more visually interesting, or at least, bring some of that into the classroom. So this is written in P5.js, which is, hopefully, as you're all aware, a very nice library for generative art and simple games and things like that. So the idea here is that you are a tiny little blob, and the noise blob is based on Daniel Schiffman's Blobby video, which is always lots of fun to go back to. And you eat other little blobs to get bigger and bigger and bigger. Now, the idea here with the adaptation is that we are going to adapt the game's performance and behaviors to make sure that the player has a good time, that it's playable, and that it keeps going on as long as possible. So here I've got a visual of the game in progress. Now I am the little hot pink blob. I've got a bunch of other blobs basically just kind of shooting around the screen, and this is all based on physics interactions. There's no intelligence here. But I'm eating smaller blobs, getting a little bit bigger, bigger and bigger and bigger. And eventually, if I got too big with our adaptation strategies enabled, the player would scale down and then, basically lots of other things would start happening too. But this is kind of the core mechanic of the game. There are no optimizations really in terms of physics collisions or artificial intelligence or anything like that yet. That might come in the future, but we wanted to at least get a proof of concept out there. Now, the software engineering background is in self-adaptive systems and goal modeling, which we're going to now talk about. So adaptive systems are basically ways to introduce changes to your system while it is executing, or at design time, but we're focusing on the execution style here. And the idea is to basically mitigate uncertainty. And what that means is to handle unexpected changes, unexpected interactions that you may or may not have anticipated at design time, but they're now manifesting in ways that you possibly couldn't enumerate. Now, maybe a human does something silly, your computer locks up, something happens that your system has to account for because you don't want it to die while it is experiencing this thing. Adaptive systems are one way to handle that. Typically, you would reconfigure something, so change some parameters, maybe change an algorithm, swap things out at runtime to handle this uncertainty, make sure your system keeps running as long and as correctly as possible. Now, one way to do that is via a feedback loop, and there are several in the adaptive systems community. MAPE-K is one of the more common ones that are out there. There are others as well, but this is one that at least I'm most familiar with. And it comprises 4 key steps. So monitoring, analyzing, planning, and executing. These are all linked together via common knowledge. So basically, information is shared between every step of this process. So monitoring is basically keeping an eye on software sensors, making sure that your overlay knows what is happening. We do this through calculating utility values. There are other ways to do this as well, but basically, how well is each requirement performing at runtime, or each goal in the case of this paper. Next, we're going to analyze. So basically look at all of these calculations. Is some violation occurring? Or is performance kind of weakening to a point where we're not happy with it? Okay, and adaptation is required. This is what we have discovered. That goes on to the planning stage where the system comes up with either one or multiple reconfiguration strategies. So here is all of the things that this system can do to handle this problem. Okay, let's pick the best one and apply it. Execute is the stage in which that plan is applied. And what execute does is it tries to execute the plan as safely as possible. Now, for a game, safety is probably crashing or avoiding crashing or maybe minimizing weird glitches or something like that. In a more complicated or safety critical system, we are making sure human participants don't get hurt, that the system doesn't go down and lose your company $1 million per second or something like that, right? This scales to a lot more complicated systems. For here, we're basically making sure that everything keeps running smoothly. So that is the overall purpose of MAPE-K. And again, knowledge is making sure that information is shared between every process here. There's no information hiding or anything like that, at least in standard MAPE-K. Okay, MAPE-K is then fed by some sort of software artifact. In our case, we're using a goal model. You could use requirements, you could use design decisions, system architecture, whatever your fancy is. But we basically use an abstraction of requirements. Now, there are numerous types of goal models. We're using chaos in this case, which means that it's a directed acyclic graph starting at a very high level up here, refining further and further down until you hit these leaf level goals, which are typically akin or parallel to requirements. You know, not strictly written out in the formal syntax, but you could derive requirements from these. Now, with this goal model, we start very high. So basically we want to make sure that the game stays active for as long as possible. You know, let's maintain a constant frame rate. Let's make sure it's playable. How do we do that? Maximize frames per second, maximize the number of live enemies, have some possible checks for the size of the player, the enemy size, the score, make sure that the player can move, that the enemies can move, that kind of thing. Now, these are all kind of linked together via these little yellow bubbles. These are refinements. And what that means in terms of a goal model is that we're going to calculate a utility value for A here. If that is good and its sub-goals B and C are also valid, then we could say A is satisfied. This particular refinement here is an AND refinement. Here we have an OR refinement. So if B's utility value is good, and either D or E's is also good, then we could say B is satisfied. Effectively, there's a dependency on the direct children here and how they are related. There's a couple of other interesting things here too. So if you see maintain or if you see avoid, those are invariants, meaning they have to always be satisfied, not good targets for adaptation. You also see achieve or maximize or minimize at times. These are non-invariants, meaning that they can be violated, albeit temporarily. Those are going to be our targets for adaptation. If they're violated, we can adapt things to bring the system back up. If it's invariant, once it's violated, we're done. That's considered a failure. Now, how do we calculate the values for these goals? In our case, we define utility functions, which are just mathematical formulas to specify how well each goal is doing. Now, these are domain dependent. This has to be defined by a human being typically, unless you have some sort of a AI process calculating this out for you and understanding what's going on. For us, we're looking at non-invariant goals that look at frame rate, playability, is collision enabled, how long is the game going, that type of thing. So none of the invariants are in here. Two examples are utility functions for D and F. So D is going to be maximizing the frame rate. F is maximizing or at least making sure that the player can be scaled, not necessarily maximizing. I almost said that wrong there. But for D, which is frame rate, if our frame rate's greater than or equal to 40, it's fully satisfied. We are all good. If it is under 30, it's violated, right? So we're seeing here, we're maximizing FPS with 30 being our threshold. Anything in between is a linear scale. Okay, now for F, this is player size, which is playability. Very simple definition from our perspective here, but if the player's too big, it's really hard to play the game, right? So if your player size is less than half of the screen width, fully satisfied. If it's greater than or equal to the screen width or canvas width, no longer playable, goal is violated. Anywhere in between is a scaling factor here that we calculate out. So how well our game is playable, or how playable is our game, directly calculatable. And we have a utility function for each and every one of these goals. Now, our instrumentation, we developed a goal model. We developed utility functions for each goal in that model, and we added our MAPE-K overlay. So monitoring is just software sensors. How well does each metric correlate to what we defined in our goal model and its utility functions? And our adaptation engine is basically, if this is violated, do this, or if this and this are violated, do this type of thing. These can be a lot more intelligent, but for a simple project like this, the overlay is a lot simpler as well. And that also will minimize the overhead for us. Okay, now in terms of adaptive gameplay, our win condition is that the player is greater than the size of the canvas. This is not really attainable with MAPE-K active because we're trying to maximize playability of this game. In our case, this is execution time. So if the player is larger than half the canvas width, we start scaling them down fairly linearly. Otherwise, let them continue to grow. If this is violated, in which case violation is a 0, we try to adapt. Now, that means that if we have our game with the adaptive overlay turned off, it's very easy to win as long as you don't get hit by an enemy along the way. Now, in terms of our setup, we developed this again in p5.js. We deployed it to GitHub pages so that we would have a stable server running the system. I ran all the experiments in Windows 10 with Google Chrome. Firefox has been a bit iffy for me in terms of performance lately, so I wanted something a little bit more stable. There were 2 experimental treatments, one with MAPE-K on, one with MAPE-K off, and for each of those, we ran 50 experimental replicates to get statistical significance. Now, I was the one that ran that, so you could make a case for threats to validity for the developer running their game and then testing it themselves. Unfortunately, my kids were not cleared for IRB approval at that point in time. They're 8 and under, and I thought that'd be kind of a fun test for them to do, but didn't get through that in time. Maybe in the future. But our overall goal is to just demonstrate the feasibility of adapting at runtime. And what we're seeing, statistically significant in both cases here, is that this is possible. Our total execution time significantly increased with our MAPE-K overlay active, meaning that our player kept scaling up and up and up, or kept scaling down further and further and further as we went, while the enemies are still bigger than the player. So it is still possible to keep playing as long as you want to with our overlay active. And honestly, it was weirdly fun, which is a fun finding as well. And our goal F utility values, which again was that scale player, always significantly better than with MAPE-K turned off. So basically what we're finding in these results are that yes, adaptation is possible. In terms of our requirements that we developed, they are able to adapt at runtime. Now, some surprising findings that we had, I really expected frame rate to be a limiting factor. Prior games I've developed with p5.js have always suffered from graphics performance issues, and in this one, with very basic collisions enabled with not a whole lot of optimizations, it actually didn't impact the system whatsoever, which to me was surprising. Other things that we found, if you become overactive with adaptations, that does cause performance to drop, which basically means, hey, you have room for extra enemies, start spawning in new ones. Well, that causes frame rate to dip because there's now that many more collisions to check, that many more basically particles to kind of track over time. And the other thing, which was really surprising, it was actually fun to play. I'm sure most of you that have developed hobby games are aware that after you get past the fun point of coding, it becomes a slog to test, and then it actually becomes real work, right? To me, this was actually quite enjoyable, which was surprising. All right, so what's next for this paper? Obviously, this was a short paper, proof of concept. So deeper gameplay, more adaptation strategies, basically fleshing out this test bed for future deeper empirical experiments. Other things we'd like to bring in is runtime search. So online genetic algorithms, novelty search, multi-objective, that sort of thing. Explore the search space of possible adaptations, and then better human studies so that it's not just the authors of this paper running our test cases. So with that, thank you to Grand Valley State and the Michigan Space Grant Consortium, and for all of you for bearing with me here. When we get to the real version, I'll handle questions, but thank you all for watching. Bye, everybody.